Hello, everyone. I have the pleasure to introduce Clarice Poon. She obtained her PhD in Cambridge in 2015. She's then both been in Paris and in Cambridge, and since 2018, she's a lecturer at the University of Bath. And today, the title of today's talk is Smooth Over-Parameterized Solvers for Non-Smooth Structure Optimization. So the floor is yours.
Yeah, thank you very much for the invitation to give a talk here and to everyone who joined. So in this talk, I'm going to be telling you about a kind of a nice way of rewriting optimization problems like the lasso into kind of smooth optimization problems for which you can apply very standard tools like L-BFGS. So this is joint work with Gabriel Pele and is based on these two references. So let me just begin with some motivation about where the kind of problems that I'm interested in come from. And so the setting where these problems arise is typically ill-posed inverse problems. So as a simple setting, you can consider solving for beta, x beta equals y. And if x is a very short and fat matrix, then you have a lot more unknowns, n, right, than observables. And this is ill-posed because there could be many solutions here. And you can also have ill-posedness coming from noise in your data and no condition of your matrix X. So some very simple examples of this. So this arises in a lot of practical applications. So for example, in painting, so art restoration, so you have some nice image and it's been degraded, and so you've got these missing parts you want to fill in, and obviously you can fill it in however you like, but there are some kind of natural ways in which you may want to fill in this missing parts. So in this case, X will be some masking operator. Another example is in magnetic resonance imaging, where in MRI, you want to reconstruct some image, let's say this brain image from samples of the Fourier transform. And if you want complete Fourier information, it means having the patient to spend a lot of time in the MRI scanner, which is undesirable. So in practice, you always have undersampled Fourier data. And so for the same Fourier measurements here, you would have two images, both of which would generate the same Fourier data, but obviously this one on the left here, to us is a better solution, right, than this one on the right here. So in this case, X would be a subsampled Fourier operator. And when we have an ill-posed inverse problem, one way of approaching this is to formulate it as an optimization problem. So you would minimize some loss function between x beta and y, and you minimize over beta. So for example, L could just be the quadratic loss. And since I mentioned there could be many solutions in this case, you want to formulate this optimization problem, so you pick one particular solution. And the very classical example would be simply you add a regularizer, which say is the quadratic term. So in this case, you make a problem strongly convex, there's a unique solution, right? But in general, for the quadratic, it doesn't enforce any kind of interesting structure. And there's a wealth of work out there on that kind of non-smooth regularizers, which would kind of impose some kind of interesting structure on this vector beta. So for example, in imaging, quite often we're interested in sparse reconstruction. So in the kind of like cell imaging, you may actually want to localize some cells which are really sparse. So this is fluorescence microscopy. Or for natural images, they're often sparse with respect to some domain, say a wavelet domain. And it's known that the L1 norm would promote sparse solutions when you minimize something like this. And so in this talk, I'm going to be telling you essentially about how to deal with these kind of optimization problems. And there has been a lot of work over the last 20 years on this already, but I'll tell you a way of rewriting this into a smooth problem for which you can apply various classical tools. And just a few comments on this operator X when it comes from an inverse problem is that quite often this operator X here is actually coming from the discretization of some continuous operator. So in the MR example just now, it was, for example, discretizing some continuous Fourier operator. And typically, if you want to have a very accurate solution, you may need to take discretization to be very fine. And so you have, first you have discretization effects from discretizing. The second is that you may want to take n discretization to be very large. And this is problematic because then the columns of X here are highly coherent with each other. So the inner product will be very close to 1. And the last difficulty with these kind of optimization problems is that the regularizer term I had just now is if you want to impose some kind of interesting structure, is typically non-smooth, right? So you can't just do something like gradient descent on it. And so, as I mentioned, there has been many algorithms for dealing with this kind of problem. And as a simple example, let's focus on the lasso, where you have quadratic loss and L1 regularization. And a kind of a very basic algorithm is iterative soft thresholding, where you essentially deal with this L1 term by a proximal step, right? So this is simply doing, this algorithm is simply doing gradient descent on beta with respect to the smooth part. So this here is the gradient of this quadratic term. And then to handle this non-smooth L1 term, you do a backward step. So you find a guy that's closest to beta hat while minimizing the L1 norm. And in this case, it has a very nice closed form expression. It's simply a soft thresholding operator. And a lot of algorithms to deal with these kind of non-smooth optimization problem are proximal based. So for example, there's primal due, ADMM, forward backward, or iterative soft thresholding, as I'm showing here, or Douglas-Rachlet splitting. And so a couple of comments about this is that, so for forward backward, probably one of the best known convergence rates is that the objective for this algorithm would converge like some constant divided by k, where k is the iteration counter. And something to bear in mind is that this constant here is essentially the Lipschitz constant of the gradient of the smooth part. So in this case, it's going to be the spectral norm of X transpose X. And typically, if X here is the discretization of some continuous operator, then this constant here grows as you refine your discretization. So as n, the number of discretization points increases, this number will grow. So these convergence rates are not really so interesting in a very fine grid setting when you have very fine discretization. So for example, if you may want to kind of, if you want to handle a kind of very typical super resolution problem where you're trying to recover, say, 3 point sources from low Fourier frequency data, this corresponds in the setting to a very fine discretization of a Fourier operator. And in this case, this constant will grow like n to the power of d, where d is the dimension that you're discretizing, and n is the number of grid points in each dimension. And there has been, I'll say more about this later on, but there has been a lot of recent work on trying to understand the behavior of these algorithms in a very fine grid setting, because these kind of rates are simply not relevant there. And so what I'm going to show you in this talk is an alternative way to handling these kind of non-smooth optimization problems by essentially turning them into a smooth problem. So there are two main things I want to show you. The first is how you can over-parameterize to obtain a smooth but now non-convex problem. So previously it was a convex but non-smooth problem, and I'm going to iterate the two. And once I've done this, I will show you how you can put it into a bilevel form. And the reason why we would want to do this, you see, is that it will lead to much better problem conditioning. And as a result of these two things, I have a problem which is just a smooth optimization problem, and I can throw very standard tools that is, so I can just simply do L-BFGS or quasi-Newton type methods to obtain fast convergence behavior. And to explain this, I will simply focus on the lasso, so where you have quadratic loss and L1 regularization. But in fact, as you see at the end, this idea can be applied to many other popular settings, such as having total variation, group L1, or nuclear norm regularization. This would be to impose different kind of structures like low rank, or sparse gradient. And you can also use this technique for also non-smooth losses, for example, the L1 loss. So now go to the main idea of how you over-parameterize and kind of refactor to make it better conditioned. So the idea is actually very basic. It's simply the idea that the absolute value function can be written as the infimum over all the quadratic curves which lie above its graph. And just as a side remark, in case you're aware of this, this kind of observation is used to derive a lot of iterative reweighted least squares problem. But of course, there's an issue here, is that with this approach, you have this 1 divided by eta, so you have this singularity eta. But you can get rid of it if you make a simple change of variables. So if I let u be beta divided by square root eta for u squared here, and v be square root eta, then that's v squared here. So it's also the same as infimum over u beta equals u times v of u squared plus v squared divided by 2. So if I take my problem now and I stick this parameterization into here, right, then you see as a simply minimization problem over u and v, written in this way. So this product term here means it's pointwise multiplication between two vectors. And so now here we've got a smooth problem, right, in u and v, but it's non-convex because of this product term. And this in itself is not new. It's been observed many times before. And at this point, you can either do alternating minimization, which is nice because the minimization problem over u is a quadratic problem, and the minimization problem over v is again a quadratic problem. So each step corresponds to solving a linear system. Or you can do directly gradient descent on u and v simultaneously. And so this in certain cases can lead to very fast convergence behavior as well. And I'll say more about this later on. But so that's this is first step of the over-parameterization to a smooth problem. And the second step is I'm going to put this into a Bilevel form with the goal of making this better conditioned. And so step 2 here is the idea of reparo. And is again a very classical idea from the late 70s due to Golub and Pereira. And the idea is that if you have a minimization problem of a function f over two variables, u and v, then it's the same as if I put one of the minimizations, so the minimization problem over u, on the inside. Right, so it's the same as minimizing this little function, little f, which I define to be capital F evaluated at this uv and v, where uv is the minimizer of this function f, where v is fixed. Right, I've simply moved one of the minimizations on the inside and defined a function little f in terms of v in this way. And the thing is, if f here is a smooth function and is in the minimization problem has a unique solution, then you can very easily compute the derivative of this function little f here. Is simply the partial derivative of capital F with respect to v, evaluated at this minimizer u here. And this is nothing more than the chain rule, right, applied when you differentiate this guy here, because the second term it just disappears because u is a minimizer of this term here. So it's easy to compute the gradient of this function f, provided you can solve this inner minimization problem easily. And the reason why you would want to consider this is that the Hessian of this function f is the short complement of the Hessian of the full function f. And it's known that the short complement is always no worse condition than a full matrix. And in practice, the Hessian of this function f can be much better conditioned than the Hessian of this capital F here. And so in general, if the cost of solving this inner minimization problem is relatively small, it can be very efficient to actually handle this VARPRO formulation. So VARPRO stands for means variable projection. This projected form, then directly handling the full guy. So if I now take this idea and I apply it directly to my lasso problem, then, so as I said, I had this UV parameterization, so this is my function, and then I define my little f to be the minimum over u of this guy here. And its derivative is simply the partial derivative of this thing here with respect to v, as this guy evaluated at v and the minimizer u. So if I look at the minimizer over u here, then it's a least squares problem, and it has a closed form solution as a solution to a linear system. So this u here is simply the solution to this linear system here. And this here is an n by n linear system, where n is the number of columns of this matrix X. And just by a matrix identity, you can also rewrite this inversion as an m by m linear system, where m is the number of rows of your matrix X. So we have two equivalent ways of writing the gradient, and which one you would do depends on which dimension of your matrix is smaller. And so a couple of comments here is that in both cases, you either handle an m by m or n by n symmetric positive definite linear system. So you can do something like a conjugate gradient, or elastic factorization to solve this. And the other kind of interesting thing is that here, the gradient is still perfectly defined if I let lambda equals 0 here. And the setting of lambda equals 0 corresponds to a basis pursuit setting, where the minimization problem is actually a minimum of L1 norm subject to x b equals y. So now in the case of lambda equals 0, it's essentially a problem where both your loss term and your regularization term are non-smooth. Right, the loss term is now the indicator function on x b equals y. And so if in that case, in fact, you can still turn this guy into a smooth problem, a differentiable problem, and have a well-defined gradient. So you kind of have this very natural handling of the optimization problem as lambda goes to 0. And so here on the right here, I'm just showing you the kind of the difference in the evolution of the coefficients when you apply ISTA versus simply doing gradient descent on this formulation here with this gradient computation. So here the setting is that I have a problem of just size 10, and each line corresponds to the evolution of one of the coefficients as I increase iteration. Right, so for iterative soft thresholding, you see that eventually your problem is basically three spots. So this guy here, this guy here, and this guy here, right? And if you look at the evolution of the paths, they move along these like piecewise smooth paths. So in particular, this red coefficient here, it starts off at the wrong sign, right? This black line is 0, and it hits 0, and then it stays at 0 for a while before leaving it. And whereas in contrast, if you do gradient descent on this functionality f here on this var-pro formulation, then we observe that you have these, the behavior is very different. You have these very kind of smooth evolution of the coefficients. And so this guy here started the wrong sign, it's jumped straight over 0 before converging to the correct sign. Okay, so in terms of, so now I'm going to tell you why what we propose can be a good idea. And so the first point is that, okay, we've turned it from a convex but non-smooth problem into a smooth but non-convex problem. So how bad is this non-convexity? And the first point is that this non-convexity in the case of a lasso doesn't matter at all, because you can show that all the stationary points of this function, WF, are either global minimums or strict saddles, meaning that your Hessian has at least one negative eigenvalue. And it's known that modes of methods like trust region methods always avoid strict saddles, and for gradient descent with probability 1 on random initialization, you always avoid strict saddles, so you always converge to a global minimum. And the second comment is that we already know from the work of Golub and Pereira that it's nicer to look at this var-pro formulation, because the Hessian of the short complement is always no worse condition than the Hessian of the full function. And in the case of a lasso, we can also quantify how much you actually improve. And so you can show that the ratio between the condition number of Hessian of F and the condition number of Hessian of the full guide. So previously I wrote capital F, now I write G, but it's supposed to be the same thing, is order lambda. So essentially, the smaller the regularization parameter, the bigger the improvement you see by doing this var-pro formulation. And the last comment is that, as I mentioned earlier, for iterative soft thresholding, the Lipschitz constant of the gradient of the smooth part will deteriorate as you refine the discretization, if x comes from the discretization of some continuous operator. And in fact, we can show here that for our functionality f, the Lipschitz constant of the gradient of this thing is actually independent of the discretization. So if x here is the discretization of some normalized continuous operator, so normalized means that x has the norm of the columns of x is just 1, and that's the only constraint, then actually the discretization is independent. The Lipschitz constant of this guy here is independent of this discretization. So you can obtain convergence rates in the gradient which are discretization independent. And I would say that in practice, this kind of approach is very efficient for very finely discretized, in the very fine grids setting. And the final kind of remark about what's going on with this method is that it has a kind of relationship to proximal mirror descent. So let me first say a few words about what this is. So in the case where you want to minimize something like this, so you have some loss function which is differentiable, and you have an L1 term, you can do iterative soft thresholding, or it's also called proximal gradient descent, right, which is this thing. And if you're actually minimizing in a Banach space, then this gradient, it lives in the dual space of this Banach space. And mirror descent is essentially where you have a potential function, eta, which is strongly convex and smooth, such that the gradient of eta is going to map beta into this dual space. So it's essentially doing descent in the dual space where through this mapping rad eta. right? And so in the case of where this eta here is just the quadratic, these two are exactly the same. Rad eta is just identity. And recently, there's a very nice paper by Shizat, where he looks at the behavior of these methods in the case where you have a very finely discretized problem. And so what he showed is that if you look at this quadratic term, so it's just ista, then actually the convergence rate is k to the power of -2 divided by d plus 2. So k here is the iteration count, and d is the dimension you're discretizing. So in the case where you're in dimension 1, is k to the power of -2/3. And in the case where you have this hyperbolic entropy function here, then he shows that the convergence rate is essentially order 1/k here. And this here is independent of how finely you discretize your problem. And so one could ask for our proposed method, this var-pro formulation, if you were to simply do gradient descent on it with fixed step size, what kind of convergence rate can we expect to see? And so I don't have any proof of this, but here's a numerical example to show what's going on. So here the example is that I'm considering the lasso. So this is quadratic loss with L1 regularization, where the operator x, so sorry, AI should be xi here. The columns of my matrix X here are these guys here. So I'm very finely discretizing a Fourier operator where you observe m frequencies. And n here, the number of grid points here is 500. And so on the left here, I'm showing the, so this is iteration count against objective value error in log scale. And so iterative soft thresholding is this pink line here. And you see it's basically parallel to this dotted line, which is the k to the power of -2/3 line. And mirror descent here with the hyperbolic entropy function is this red line here. And you see it's almost basically parallel to this dashed gray line here, which is the 1/k line. So that's the result of Shizat, linear Shizat. And so if we take our formulation where we have this UV parameterization, so that's what I called Hadamard, before I do var-pro. So if I simply do gradient descent on U and V at the same time, then that's this blue line here. And you see it's basically parallel to this dotted 1/k line again. So it's essentially all the 1/k behavior. And var-pro again is this blue guy here, and this again is parallel to this 1/k line. So numerically, we observe that if you simply do gradient descent with fixed step size, you obtain the same convergence behavior as mirror descent with this hyperbolic entropy function. And there is a interpretation here. So for mirror descent, without the proximal term, is this guy here, right, where eta was the potential function, and f, if you're minimizing with respect to f. And if I divide by tau and let tau go to 0, so the associated ODE with this guy is this thing here. And so if we come back to the lasso, where I've got my UV parameterization, right, then, and I do gradient descent on U and V simultaneously, and I let the step size go to 0, then this is the associated ODE. And so if you were to look at beta, define this to be UT times VT in the pointwise sense, then you can show that d by dt of gradient of eta gamma t, beta t, is equals to -2 grad f of beta t. Right, so here, this here is exactly the mirror descent ODE with entropy function eta gamma t. It's just that this potential function, it changes with time and is exactly the hyperbolic entropy function. And so gamma t here, it goes to 0 as time goes to infinity. And so you see that when gamma here is very large, it kind of resembles a quadratic bit. And when gamma becomes very small, it becomes, this guy here becomes closer and closer to the absolute value function. So the point is that implicitly, if I look at beta equals u times v, it is implicitly being optimized in hyperbolic geometry. And what I mean is that by this is that for mirror descent is doing optimization with respect to a different metric, right? So for just a gradient descent, you're simply doing descent with respect to the Euclidean norm. And for mirror descent, it's kind of doing descent with respect to a so-called Bragg distance that's defined by your entropy function eta. So implicitly, we have this relationship to mirror descent. But if you simply do gradient descent on u and v, it's simply doing descent with respect to the Euclidean norm. And because we're simply operating in Euclidean geometry, it means that we have at our disposal a lot of nice tools from standard smooth optimization, like Bilevel and step size, quasi-Newton methods, BFGS, and so on. And so BFGS is essentially a kind of low rank, kind of Newton's method where you have a low rank approximation to the Hessian. And what we find to be extremely effective in practice is if you put your non-smooth problem into this VARPRO formulation and you simply give it to a L-BFGS solver. So now let me show you some numerical examples. And a disclaimer for what I'm about to show you is I'll show you some computational time against objective value error. And of course, this is run on my laptop, and where possible, I use the code of the authors who wrote their method. So some kind of benchmarking just to show you a bit what's going on, but you can argue it's not the most fair way of doing it. It's just to give an idea of how it works. Okay, so here, the first problem is a lasso problem. So I took some data sets from the SVM website, some standard benchmarking data sets. And so here I'm just taking a problem which is highly overdetermined. So this is a kind of regression problem. And so here we benchmarked against a lot of methods out there. For example, Seller here is a state-of-the-art coordinate descent method, and we also benchmarked against FIST with fast version of iterative soft thresholding with Bilevel and step size. So these graphs are showing computational time against objective value error for different regularization parameters. So going from relatively large to smaller and much smaller. And lambda star here is the optimal regularization parameter found by cross-validation on the mean squared error. And so our method is what I call non-convex pro, is this blue dashed line here. And something we observe is that its behavior is kind of quite independent of the regularization strength. And for the methods such as Seller here, Seller is actually performing very well when the regularization parameter is relatively large, but you see that as it gets smaller, right? This red line is Seller, the performance deteriorates, right? In this case, FIST with Bilevel and step size, this was kind of a restarted FIST is actually one of the fastest methods here. Right, it's this blue line with crosses. And this here is an opposite setting where is a highly underdetermined problem, so a short factor matrix. And And again, our method is this blue dashed line here, and again, performance is it's quite independent of your regularization strength. And here, Sulla is the is extremely fast, right? It's this red line down the left hand side. And on the other hand, Vista here, it is very fast when there's high regularization stress, but as it decreases, it deteriorates a bit. Right. So I would say one good thing about methods is that it's very simple to apply, and there's basically no parameters, so you have to tune here when you do the optimization. Okay, so what about other regularizers? So as I mentioned, this regularizer here is used to promote different kinds of solutions. So other regularizers you may want to consider, that the people typically consider, for example, would be L1 of the gradient if you want to have sparse gradients, so you want piecewise constant solutions. Or you can do things like low rank if you're minimizing over so nuclear norm if you're minimizing over matrices, and so this is some of the singular values of your matrix, and this promotes low rank solutions. Or one may consider group L1. So if groups of your coefficients are supposed to be sparse, then you can do this 1-2 norm, where you take the Euclidean norm of each group and then you sum them up. So the group size is 1. This is simply the L1 norm. And in fact, you can do exactly the same thing for all of these regularizers. And so the key point, the sort of first step where I did this over-parameterization was this quadratic variation of form. And in fact, the group L1, the LQ norm for Q between 0 and 2, or the nuclear norm, they all have this kind of quadratic variation of form. And this a general result on this actually goes back to some early computer vision works. And so you always have you can always write a regularizer in this kind of quadratic variation way, provided that it is the composition of a concave function applied to beta squared. So if you can write your regularizer in this way, then you can have a quadratic variation of form. And that's the case with a lot of the popular regularizers out there. And so a kind of general formulation, if you have a regularizer which has a quadratic variation of form, and you assume this function h is differentiable, and some convex loss function L here on x beta, is that, again, you can simply write it. You can simply plug this formulation into your regularizer. And in the end, if you manipulate this a bit, you can say it's a minimization of a function to f defined in this way here. So L star here is the convex conjugate of L here. And if we simply look at the derivative of this with respect to v, you can see that it can be written in this way here. And so just intuitively, its gradient is this guy here, where alpha v is a maximizer to the inner problem. And you can show that if your loss function is C11, so it's differentiable with Lipschitz gradient, then you can prove that this function f is actually differentiable. Or in the case where this here is constraint, so for example, this is indicated function y, so it corresponds to having constraint of x beta equals y. You can show that it's differentiable at the point v, provided that your problem is actually feasible in the first place. So there exists some beta for which x beta equals y. And you're differentiating at the point which contains the support of the true solution. And I think I'm supposed to finish in the next 4 minutes. Is that right?
Yeah, I think you can go on for 10. That wouldn't be a problem at all.
Oh, okay. Yes. So, for example, in the case of total variation, oh yeah, sorry. And you see that if you want to compute this gradient, you have to solve this in a problem here. And in the case where L here is the quadratic term, then this here is simply a kind of a least squares problem again, and it has this closed form solution as the solution to a linear system. Right, so in the case for total variation denoising, so D here is say a finite differences operator, and you're trying to find a piecewise constant solution. Then in this case, alpha V is a solution to a linear system in this way. And VK here was this gradient here, right? And so here is a kind of like a weighted Poisson problem that you have to solve. And this here is a typo, it should be D. Okay, and actually, in this case, there's a very natural kind of competitor, is that you can simply write it this thing here. If you write down is dual problem, is this guy here, so you can apply projected gradient descent to it because you're minimizing a smooth guy over this constraint. And so another standard approach is simply do projected gradient descent, and you're doing then the dual variable is alpha k, and in both cases, there corresponds the primal variable in this way. And but in practice, I think due to much better conditioning of this problem, you would see much fast convergence if you were simply doing this here with fixed step size tau. So here, the top row is simply doing kind of gradient descent with fixed step size tau. And you see that by iteration 30, you basically converge to the actual solution, whereas for proximal gradient descent, when your discretization is very fine, even by this convergence is much slower, right? By iteration 9000, you're still not quite converged here. Okay, so here's an example for group sparse regularization, so this L1-2 norm. And so this example is an MEG-EEG problem. So you're trying to locate some sources in the brain from MEG-EEG data. So you've got all these sensors around the skull. And you assume that your sources so you have time series measurements, and you assume that sources, they don't move over time. So you end up with these this group sparse structure, because so this is where, for example, one source will be active, right? And it stays in the same position over time. And so we took the experimental data from a previous paper. And so here the problem is that you have this time series data, right, at these MEG-EEG sensors. And so this is the number of observations, right? It's number of sensors times 181 time points. And here you have got this many, 2,294 source locations, and again, so the number of unknowns is the number of source locations times the number of time points. And so again, it's objective value error against computational time, and we use the code of the original authors that we compare against for different regularization strengths, going from largish to small. And so there's orange guy is Seller is a coordinate descent method where you have support pruning, and it's very fast, right? When you have large-ish regularization parameters, and it deteriorates as the regularization parameter gets smaller. And the other ones we compared against was 0-MeM-SL1, which is kind of a proximal quasi-Newton method. That's this black guy with circles, or Pfister with BB step restart and restarts. And then this is this light blue line with crosses. You can also do things like optimal transport computations. So this is where you want to compute the distance between two probability vectors, P and Q. And it's interesting as a loss function in, say, like seismic imaging, where we want to preserve the densities of what you're optimizing over, and it's now used a lot as well in machine learning, where you want to compare the distances between objects, and you somehow are able to write these objects as a probability distribution. So here in this setting, the Weierstein-1 distance is written this way. So P and Q, they're your probability densities, and so you're minimizing over the flux vector, such as divergence of this W is equal to P minus Q. And if you were to discretize this, and so if you're dimension 1 or you're in a graph, then so X here is going to be this divergence operator. And in the case of dimension 1 on a graph, this corresponds to an L1 regularization term subject to a linear constraint. And in the case where you're in high dimensions, right, W is a vector in RD, and so this is kind of like a group L1 term subject to linear constraints. And so here we did some computations for the transport distances on graphs. And since we've got two non-smooth terms here, a natural alternative method is primordial splitting or Douglas-Reschert splitting. And for these other methods, for these splitting methods, you typically have at least one other parameter that you have to tune in your method. So here I'm just showing for a range of different parameters. So PD is primordial, DR is Douglas-Reschert. And our method is this blue dashed line. And I would say that for a good choice of parameters, right, primordial is very fast as well. But one nice thing here is that we don't have any parameters to tune when you simply throw our function to a L-BFGS solver. And this is an example for total variation in painting. So here we're doing group TV, so is essentially 2-1 norm applied to the gradient for colored images. So T here is the number of color channels. So in this case is 3 for RGB. And DH is the horizontal gradient, DV is the vertical gradient. So in this case, X is a masking operator, and again, the comparisons are against primordial and ADMM, and these methods, again, they have different parameters that you have to tune. And this is the size of the image that we did the experiment on. And again, it's for different regularization parameters. So this here is really just to show you that our method can be applied in this setting. It probably is not the best method that you want to use, but since I would say you're interested really in this initial phase where primordial and ADMM are performing very well, but I think one nice thing is that we don't have any regularization parameters to tune here. And it kind of works at this resolution. Okay, so, and this is another example with hyperspectral imaging. So it's the same as before, but now we've got essentially 224 color channels. And I will say for this experiment, especially when you have very large groups, our method seems to perform very well. Again, is our guide is this blue dash line. And the comparison against primordial and ADMM as before. Okay, and maybe one last example. You can also do this for low rank regularization. So if you're minimizing over matrices, then the nuclear norm, so the sum of single values, promotes low rank solutions. And so the setting here is a multitask learning setting. So normally for supervised learning, a simple setting is you're given data points, xi's and yi's. You want to find some vector beta, so just a linear function essentially, which maps xi's to yi's. And in the multitask setting, you would have data points not from one task, but from t tasks. So for example, you're trying to predict the exam performance of students not at one school, but at multiple schools, at t schools. So you're given data from t different tasks. And you want to find, for each of these tasks, you want to find a function which is going to map xti's to yti's. And so we took the setting shown from this paper here. And in this case, if you want to find a linear function with and assume that they're somehow correlated. So they're related by some matrix U here, which is unitary. Then it corresponds to a group, to a low rank regularization problem where this here is a nuclear norm. So we took 3 very standard data sets here. And in this case, you can do Vista with 3 starts. This black line with circles, or the method proposed in the previous paper was iterative related least squares. And there you've got some kind of parameter that you have to decrease. And so these are just 3 very standard data sets, and our method is this blue dashed line here. It's performing less well for this last guy here, but then you notice that the time scale is much smaller here. And in a sense, it's a much easier problem because here you have a lot of data points for this last problem. Okay, so I think I will stop here. So what I showed you is that what I presented was very simple. You can simply convert a non-smooth but convex problem into a smooth but non-convex problem. And if you then put it into this bilevel form, you improve the problem conditioning. And it leads to a very simple algorithm for which you can simply apply L-BFGS to. And you can actually do it for a wide range of settings. And although I didn't show, you can also do it for any non-smooth loss for which you have a quadratic variational form. So you can include a case where your loss function is, say, the nuclear norm or the, a group Lasso term, a group L1 term. And in terms of why this is a good idea, is that in general, VARPRO improves problem conditioning of the Hessian. And for the lasso or group lasso, we can characterize this. It's non-convex, but it doesn't really matter because all the saddle points are either global minimums or strict saddles. And we've got this kind of relationship to mirror descent. And since the Lipschitz constant gradient is dependent of the discretization practice, it performs very well when you have a very finely discretized problem. And yeah,
sorry.
Yeah, I think that's everything I wanted to say. So thank you very much for your attention.
Thank you very much for the very nice talk. If there are questions from the audience, please just unmute yourself and post them. Maybe I can start with one.
Mm-hmm.
So the main idea here is to turn these non-smooth problems into smooth problems through the Hadamard parameterization. Have you thought about, maybe this is a completely stupid question, but what would happen if the original problem is smooth in itself? Would you obtain the same rates, or would something strange happen?
If the original guy is smooth, but you have this.
Are there even cases where this can be done?
You can use this idea, I guess, as long as you have a regularizer, which is a concave function applied to beta squared. And I think in these early works, for example, they have got these regularizers which are very flat here, and then you can imagine that you smooth out this part here, then it becomes smooth. And I think in these original works, the advantages of putting it into these bilevel forms, sorry, these quadratic variational forms, is actually more in. This was actually the formulation where they considered, so it's still non-smooth because it's 1 divided by eta, but it's more to handle very flat gradients. I can't really tell you what advantages I would bring in these settings. Yeah.
Okay. Are there more questions? If not, then I will thank you again, Clarice, for giving the talk in this seminar.
You're welcome.
Thank you.